Yeah. Okay, so yeah, thank you everyone for coming here today. So today we're going to be talking about spontaneous symmetry breaking. And this will be kind of a continuation of last time. So let me briefly recap what we discussed last time. So last time we introduced mean field theory. And in particular, we use the example of ferromagnetism. So we have an order parameter. Which was the average magnetization per unit volume. And this we assumed that this was proportional to, well, it's aligned in some direction, which if we apply a background field, which I'll denote small h, the magnetization would be aligned with that background field. So the situation in ferromagnetism is as follows. So the system behaves differently above and below a critical temperature. So above critical temperature, the spins of the electrons that are unpaired in the atomic lattice, they are pointing in random directions. So the spins are aligned in random directions. But below this critical temperature, they are all ordered. They are aligned in some direction. And if there's an external magnetic field, they would be aligned with that field. But even when there's no external magnetic field, they will be aligned in some direction. So we describe this using the free energy density and expanding it as a function of this m. And since we expect the system as a whole to be rotationally symmetric, we expand only in even powers. So we can have some constant plus some linear term and then the next, a quadratic term, there's no linear term, and then a quartic term, and it could go higher, but for now we'll stop there. And if we want to apply an external field, which I'll denote little h this time, this would give a linear coupling like this. And then near the critical temperature, we can identify this coefficient little t as being something that changes sign at the critical temperature. So for example, T minus Tc over Tc. And this is a phenomenological model. So we just introduce some unknown parameters, and then we try to fit them to data or fit them to our understanding. And then this parameter u will be some constant term plus other pieces that are of order t minus tc. So if we're near the critical point, then we can just keep the leading contributions. And then we want to minimize this. So df by dm at some m bar should equal 0. This is t plus, t m bar plus 4u m bar cubed minus mu0 h. And then when the external field, small h equals 0, this has a solution, or this has two solutions. So m bar can be, it's minimized for m bar equals 0 above tc. And for some non-zero constant, plus or minus square root of minus t over 4u, for temperature below tc. And then we can define critical exponents. Which is basically the behavior of various parameters near the critical point. So in particular, this m bar is proportional to tc minus t to some power beta. The magnetic susceptibility is proportional to t minus tc to some power minus gamma. The magnetization is proportional to, at the critical point, is proportional to any applied external field to the 1 over delta. And we can compute these. For example, the susceptibility is given by, well, 1 over the susceptibility is given by dh by dm. And we take this in the weak field regime, which we can say is for h equals 0. And from this equation that's satisfied at the minimal, we find that this is, I guess there's a irrelevant 1 over mu0, and then t plus 12 m squared, m bar squared. And then depending on whether we are above or below tc, this will either be t or minus 2t. And this tells us that since this small t is proportional to t minus tc, and this is susceptibility to the minus 1, so susceptibility goes as 1 over t minus tc. So this gamma, which has a minus sign in front, would be 1. And then similarly, we can read off that again from this equation, at the critical temperature, this first term vanishes. So we see that H is proportional to magnetization cubed, or in other words, I'll just put it up here. So at equals TC, this average magnetization is proportional to H to the 1/3. So this delta equals 3. And I want to now note at this stage that that rotational symmetry is spontaneously broken by this non-zero magnetization below PC.
So the should the critical exponent be a rational number?
Not necessarily. I mean, yeah, actually, I'll come back to this point at the end, hopefully. I mean, experimentally, you can measure all sorts of numbers. And there's a question of the validity of mean field theory that I'll come back to.
I'm sorry. So
Yeah.
before we are heading on, but just wondering what's the exact meaning of mean field theory and why we need it in this story?
So it's so when we have a system like a ferromagnet that has many atoms, it's very complicated, and the origin is like due to some quantum mechanical process. So this is like some phenomenological model that we want to apply by just taking a continuum approximation by coarse graining over all this small structure and just capturing like the macroscopic large scale effects of the theory. Yeah, so basically, yeah, so it's some kind of leading approximation to the large scale behavior.
When we deal with some average things or statistical things, then we can say that we are use mean field theory.
Yeah, it's it's the leading term. So what I'm going to talk about today is like going beyond this this leading contribution, which is still mean field theory, but then we will also consider fluctuations and how they behave as well. And I should also mention that I'm using ferromagnetism as an example, but mean field theory can be applied in well, various dimensions and various field dimensions, and it can be applied to many different types of systems, like superconductors and superfluids and other things.
So when you say that the rotational symmetry is broken spontaneously, how do you see this from the equation? I mean, of course, if you have an external field, the external field breaks explicitly the symmetry because you have a preferential direction. But and then, of course, when you switch the external field off, you still have the magnetization persists, let's say. But this is not exactly what we have in mind when we think about spontaneous symmetry. When we think of spontaneous symmetry, we think about some degeneracy, and the system basically chooses a random point.
Yeah, I'm going to a little bit further on. I'm going to draw a picture, and all this will become very clear.
I see. So this is just an anticipation.
Yeah, this is some kind of foreshadowing. So okay, so now we want to go beyond mean field and look at the fluctuations, and this is where we will start to make contact with the usual picture of spontaneous symmetry breaking. So beyond mean field. So I also want to kind of recap one more thing from last time, which is the microscopic origin of ferromagnetism, and that was due to an exchange interaction. So this kind of spontaneous magnetization is a result of the spins in the atomic lattice interacting with each other. So we can consider the exchange interaction between two electrons. So the state or wave function of a combined pair of two electrons can be in one of two states. It can be a singlet state, or it can be a triplet state. And then the singlet state has a symmetric spatial wave function and an antisymmetric spin wave function, which gives for which there is only one possibility. So this is a singlet, and then the triplet is a combination, conversely, of an anti-symmetric spatial wave function and a symmetric spin wave function, which is a triplet because spin can be, the combined spin can be +1, 0, or -1. And then if we consider the operator S1.S2, this we can rewrite as 1/2 of the total spin squared, so S1 plus S2 squared minus S1 squared minus S2 squared. And then if you recall that the eigenvalues are of the form S times S plus 1. So then, since we know that in both cases, the total spin of each will be one half plus 3/2, or 1/2 times 3/2, sorry, is 3/4. And then if we plug it in and do the calculation, there are two possibilities. One is -3/4, and this total spin can be either this eigenvalue can be +2 or it can be 0. So combining everything, we get -3/4 and 1/4. So this is for the singlet. And this is for the triplet. So we can write down an effective Hamiltonian of this in a kind of fun way by just saying that this is the energy of the singlet state times something that vanishes when it's in the triplet state, which would be 1/4 minus S1 dot S2 plus energy of a triplet state times something that vanishes in the triplet state, which would be 3/4 plus S1 dot S2. And this will be some kind of constant, which we don't care about, minus what I'll call J S1 dot S2. And J here is singlet energy minus the triplet energy. So this is the type of interaction that we want to deal with. And this was a very quantum mechanical calculation. But I'm now going to be slightly cheeky and use a classical approximation to relate this to the continuum theory. Yeah.
So here you are totally, so depending upon the first derivative with respect to free energy, it seems that derivative is, we can, so the point I want to ask is that your whole assumption is based on second order phase transition over here?
Yes, that's a good question, thank you. So this is a theory that applies to second order phase transitions.
So because if it is a first order, then that derivative would not have been possible, right? df by dm.
Right, indeed, it would have a
So the whole
singularity.
calculation is based on second order phase transition.
Right. Yeah. Yeah, so in this case, I didn't talk about the specific heat, but if you check it, it will have some kind of kink.
Yeah, yes.
So at T equal to TC, this is a prediction or an assumption?
Sorry, this one here.
Yeah, T equal to TC. So the transition.
Yeah, I guess this is a phenomenological model that we want to. Yeah, this is kind of our input to this model, that we want something that where the quadratic term changes sign at the critical temperature.
The type of transition, first or second, first order or second order, through crossover, or so this is an assumption or depends on this potential.
This
It's
is
a concept.
this is a very general assumption for any second order phase transition.
And so you assume from the start it's a second one.
I should emphasize that this all applies to second order phase transition.
I think introducing that cubic term, it will break the second order, right?
Yeah, probably.
It will be purely first order.
Right. Yeah, you get introduced terms.
The cubic term, it will break the second order.
So it's implicit in putting only even.
Only
even
the.
okay. Now it's consistent.
Okay. Yeah.
Another very naive question, Stephen. The thing is that since I'm not able to relate this part of yours where you calculated difference, because if it is a second order, then my second derivative with respect to free energy will give me the heat capacity of the system.
Yeah.
So my question is that how to relate. My question is that if I take the Hamiltonian which you have defined, if I write the partition function and calculate the heat capacity, will I get back the same result?
I think you should do, because I mean that's what I want to do next, essentially. I mean, I won't talk about the heat capacity, but I will recover. Basically, I want to get the derivative term in this model.
Yeah, at this stage, the relation between the Hamiltonian and the energy is not yet fixed. So you
yeah. In fact, this is not related to anything we've seen so far, but it will be combined.
It's too early.
Yeah. So we want to take a classical and continuum approximation. And for this, what we can imagine is if we have two spins that they're pointing in some direction, and it's that's not very good, so let me try again. It should be pointing in almost the same direction. So this would be something like if we have a magnetization, it's pointing along here. So this is S1, this is site number 1, and this is site number 2, and this is S2. And we can consider some angle phi 1, 2 between them. So then, classically, we can write S1 dot S2 is S squared cosine of phi 1, 2. And then when phi 1, 2 is much smaller than 1, this is approximately, S squared 1 minus phi 1, 2 squared. And since we can think of this vector here as this is S1 minus S2, then by trigonometry, then size of phi 1, 2 is, I should say, approximately size of S2 minus S1 divided by the size of S1. And if these spins were perfectly aligned, and we think about we only have 2 spins here, but if we think about generalizing this to many spins, if they're perfectly aligned, then the magnetization would be equal to the what's known as the saturation magnetization, so the maximum possible magnetization. But if they're slightly misaligned, then we have this angle, and this small angle can be, so we can use this to relate this ratio to the ratio of magnetizations. So this can be written as M2 minus M1 size of divided by the saturation magnetization. And then furthermore, if we have a spacing between them, which I'll call A tilde, then this can be approximated as A tilde over saturation magnetization times the size of the derivative of the magnetization vector along what I'll call the x direction, where this is the x direction. So this means that our exchange Hamiltonian, well, in this classical description, we can write this as minus js squared, 1 minus 1/2 I12 squared. And we can say that this is approximately minus js squared. Minus js squared plus js squared A tilde squared for 2ms squared times dm by dx squared. And now we generalize this. So if we have many nearest neighbor interactions,
By the way, what is M bar in the above equation?
which one?
On the right side, you have derivative of M bar and T squared.
Oh, sorry. Yeah, thank you. This is this is vectors. Okay. So if we have many such interactions, then this exchange Hamiltonian will look like some sum over pairs, sum over nearest neighbors of this J, which we assume to only be non-zero for nearest neighbors. Si dot plus J. And this is approximately some constant term plus J squared over 2 sum over nearest neighbors by J of by ij squared. And then if we're so essentially along one dimension, this will pick out the derivative along a particular direction, and then we're summing over nearest neighbors in all possible directions. So in the end, what we get is that this is some constant plus J squared A tilde squared divided by 2ms squared times some sum over nearest neighbors of the gradient of this magnetic field of this magnetization, sorry, at the site I squared. And then, so if we have n sites, and then we take n to infinity, and simultaneously take the lattice spacing to 0, then this exchange Hamiltonian will, or at least the dynamical part of it, will tend towards something like some constant, which we usually put as k over 2, some integral over all the spatial directions, which we have small d of them, times just the gradient of m squared. Right, so these exchange interactions will give us gradient terms as well.
This is a position, a function of the position.
Yes, it will.
So what I mean is that you have a variable upon which you are integrating, but this h is defined at a certain point. Yeah. So in the first there, you fix I and you sum over j, right?
Yeah.
So is the potential. This is constant everywhere.
So
Yeah.
yeah, so this will,
Constant.
yeah, this will be so what I'm imagining is every pair of lattice sites you have something like this, and then yeah, maybe this is better to say sum over I, and then you have there'll be some additional factor due to the number of.
No, what I mean is that in that term you fix I, and then for each I you consider all the nearest neighbors to I,
Yeah.
and you sum upon them.
Yeah.
So interpret this is like that way, right? If I think this as like an Ising model,
Yeah.
Then this, so if I fix I and if I it will be like magnetization per site.
Per site,
Yeah.
And when I take the integration, it will be covering the entire volume of that.
Yeah. Yeah, so the magnetization M is the magnetization per unit volume. Anyway,
If I take the summation, it will not be because here J is like a hopping parameter for like just we having finite value. Like when I take the discrete value, it's like we are talking about per site of the magnetization. If I think in a discrete way.
Yeah, so I think maybe I can say this is there will be some extra numerical coefficient here.
Yeah, that will be
over this is just a sum over I over every site. And because we'll get terms, the gradient will give terms in like the x direction, the y direction, and so on.
Well, the question is simply that when you integrate that, is this over a box or infinite because you have translational invariance? But does this integral converge over an infinite volume?
Right. So I should say this is a.
No, it's not a good question, because if you said that J goes to there has something that goes to 0 beyond the nearest neighbor, right? you said that J was equal to 0 beyond the nearest neighbors. So this integral is not upon the full volume, it's just in the neighborhood of each point.
Right. So
Probably is in the volume integration in that integral.
so the volume is, you can think of some cubic lattice or some giant cube, which is L to the D, which is
So what I mean is that integral over dx, the integral is not over the full volume, is in a regional, in a small region, right?
Now we have some certain size of this.
yeah. So
Yeah, in other words, this A tilde should enter into the boundary of this integral. Or no, it's probably
Right.
no. A tilde is not what is.
so we're taking this n goes to infinity and a tilde goes to 0, and define the total volume as like L to the D, which is n times a tilde to the D.
No, wait a moment, but this is an energy density, so you divide this by the volume. In other words, you take A equals to 0. Implicitly, you divide, if this is per unit volume.
Yeah.
Okay.
Yeah. So I should emphasize that at the beginning, that this magnetization is per unit volume. So
Considering finite volume, right? So what about the boundary condition measured then?
so yeah, in practice,
For isomorphic, we usually identify such
Right,
boundaries.
you're
and
boundary
we
conditions.
use the kind of things.
yeah. I won't talk much about boundary conditions, but I mean, I guess we can either consider periodic or like Neumann boundary conditions, and
Yeah, the boundary condition.
yeah. Yeah, I think in any case, since this is a local statement, then yeah.
H is the Hamiltonian, not the density, right?
Yeah, so yeah, this is the Hamiltonian. Maybe I should call this now some capital H for exchange, which is this thing. Yeah. Okay, so I'll move on. So let's look at the partition function for the system in the continuum limit. So to recap, so for and
On your right side.
this one. Oh, okay, thank you. That's great. Thank you. So for a single degree of freedom with some energy spectrum that's discrete, some set of energies Ek, then the partition function, which I'll call Z1, is just the sum over K of the Boltzmann factors of this e to the minus beta Ek, where beta is 1 over kBt. For continuous spectrum, which I will say depends on some phi, it depends on some degree of freedom, then this just becomes an integral over d phi e to the minus beta e of phi. And now if we want to generalize this, now we have capital N degrees of freedom. Sure, by I, where I is 1 to the N, 1 to N. Then Zn, the N particle partition function, is proportional to Z1 to the N. And that means it comes out as something of the form integral of d phi 1 up to integral of d phi n e to the minus beta, and then I'll put a sum here from I equals 1 to n of the I'll now write this as the Hamiltonian so we can make contact with this discussion. And this Hamiltonian can depend on phi I. And actually, in general, it can also depend on, or let's leave it like that for now. And we'll gradually make it more complicated. So these are kind of non-interacting. But then if we want n capital D dimensional degrees of freedom, which I'll call m vector I, with exchange interactions, then our Zn, which I'll just call Z at this point, is, so there's a product from I equals 1 to capital N over the capital D dimensional integral of m I, and then we have e to the minus beta times, we can have this sort of term here, sum from I equals 1 to the n of the h mi vector, plus then we can have things like sum over I and j up to n of some exchange Hamiltonian, which depends on m I and mj, and potentially higher order terms as well. So this is the kind of maximally complicated structure we have for a finite number of degrees of freedom. But we want to go further, and we want to take the continuum limit of this. So for the continuum limit, where n goes to infinity, we want to replace these mi vectors at discrete, which we can think of as being at discrete sites in our lattice. We want these mi's to become continuous functions, or a continuous function of x. And then the resulting partition function is an infinite product of integrals, which is usually denoted as a path integral. Like this. E to the minus beta. And then these sums, as I showed before, these can reduce to integrals. So it's integral d dx of some h, which is now a functional of m of x. Where, since we're including exchange interactions, this h of m of x. Oh, sorry. No, that's fine. I'll define this as the integral of the Hamiltonian density. Which we can write as integral over d dx. Oh, so the first piece, we want something that whose leading background contribution reduces to the free energy. So essentially, we can take what we had before. So this is integral over d dx of our free energy, where now we don't assume anything about its value, but we will be applying this near some critical temperature, so we are intending to use the same kind of approximation. This is over vector m dot t over 2 vector m squared plus u times, well, vector m to the 4 or vector m squared squared. And we could have higher order terms. And then we include also the exchange interaction, which gives us something like k over 2 gradient of m squared. And we could also have higher order interactions if we, in the gradient, if we have more complicated exchange interactions between different sites. And then we include minus mu 0 little h dot m as our interaction with any background magnetic field that we want to, any external magnetic field that we want to apply.
But I still have can you distinguish between the integrated, so you have an x upon which you are integrating, is a dummy variable, let's say. Then you have an x on the left-hand side. So this Hamiltonian is constant in space, or depends.
So maybe you can just
this is an average.
I mean, not an average. It's this is x prime, some other. Yeah. So this is everything. Every x dependence is a dummy variable inside the m.
No, what I'm trying to say is that on the right-hand side, you are integrating upon x, right? So what is the dependence on x that is on the left-hand side? I'm just asking if this is invariant by translation or if there is some.
Maybe he's asking about the H.
This,
H, yes, H,
Yeah,
H,
typing.
H on the left-hand side, yes.
yeah, I think maybe this
Probably this is no dependence.
yeah, I think maybe this
It's
is
raised, that's-
Yeah, yeah,
Yeah,
exactly.
this
This
is-
was
yes,
my,
yeah.
this was my
Yeah.
point.
Thank you. Yeah.
When we perform a passive integral in quantum field theory, if you want to use the Hamiltonian, then we have to passive integrate the field variable and the Coulomb momentum, right? And
Yeah.
what is momentum for the variable m?
So actually, yeah, I've glossed over that, but I think in this case we can identify this little h as the canonical momentum.
But isn't the h a source term?
Yeah, okay. They kind of they look similar. So yeah, we have a term like that if we if we want to also include the canonical momentum, then yeah, we also have such a term.
Yeah, also we have added the m squared term and the quadratic term in m in your Hamiltonian, right?
Yeah.
It seems that the variable m, there's a self-interaction of the variable m. So what is this self-interaction?
Hmm. Well, so in terms of the magnetization of the material, I guess we can.
Maybe it might be the hysteresis? Maybe, I don't know.
I think not necessarily. I mean, I think because this term is what induces the non-zero magnetization at low energies, and that would give rise to hysteresis. So maybe I mean the combination of the two would give the hysteresis, I guess. Yeah, but it is some kind of self-interaction of the magnetization on itself. So this is known as the Ginsburg-Landas Hamiltonian. So to make contact with what we had before, I just briefly say that in the mean field limit, this the partition function in general should be e to the minus beta times free energy, which in this case is e to the minus beta integral d dx of the free energy density, which in that limit we just say is e to the minus beta times some volume times f. Okay, so now we'll start to make more contact with particle theory. Let's consider fluctuations. And Goldstone modes. Okay, so when the external field H equals 0, the Hamiltonian has rotational symmetry. In field space. And also in position space, but in particular in field space. Then as the temperature decreases below the critical temperature, non-zero magnetization M appears. In some direction. And this means the symmetry is spontaneously broken. And here, spontaneous means it's a symmetry of the theory so in particular of the Hamiltonian, but it's not a symmetry of the solution.
I'm sorry, what do you mean the not of solution?
I just mean that the solution itself breaks the symmetry.
This is, I would like to understand it because, of course, the parallel quantum field theory is evident. You have a negative mass term. This term becomes negative. But this is done by hand. This is all an effective theory. So what is the, how do I say? So the first thing is this is only valid in for temperatures very close to DC, right? Because you said that you so in other words, you are when you say above or below, you are considering very small intervals. Or
Right.
because this Hamiltonian is an expansion, you stop the expansion.
Yeah, so this approximation, so I think I won't be able to talk about it, but you can actually quantify the validity of this approximation in terms of some temperature range, which depends on and what that temperature range should be of validity. It's you can compute by expanding corrections, and it turns out actually that maybe I'll just give this spoiler now that it's actually technically not valid for dimensions less than 4. But yeah, but I think people, in some sense, people find it good enough, or sort of gives some feeling for the systems. But of course, then people want to go beyond this and do further treatment with like renormalization and considering higher operations to try and mitigate this.
Oh, and I'm sorry, I forgot that also. How can we see that rotational symmetry in the expression?
Rotational symmetry in this expression.
But because you can rotate and
So-
this depends on the square.
Yeah, m goes to some.
But the minimum of the energy is when t is negative is some you have a vacuum exploitation value for it.
Yeah, so yeah, any m goes to something like that. Okay, so then yeah, okay, I will then say that if the broken symmetry is continuous, so for example, when the field space dimension capital D is bigger than or equal to 2, then the ground state or minimum energy configuration is a degenerate manifold or to be precise, it's a manifold of degenerate ground states. In other words, there are flat directions in field space. Yeah, flat directions corresponding to each broken symmetry. Here, I'll write that. Corresponding to the broken symmetries. And fluctuations in these directions are called Goldstone modes. Or in the particle physics terminology, Nabu Goldstone bosons. So for example, if we consider d equals 2, then, well, I will attempt to draw this situation. So we have something like this. So this is M1, this is M2, and this is some, well, actually, I'll put free energy M. And then we have something like a quartic potential in both directions. Basically, this is a Mexican hat potential. So it crosses here, it crosses here, here, and then there's some kind of circle of minima like that. And it may be easier to see from a top-down perspective. So we have M1 and M2. And then at temperatures below the critical temperature, the minimum energy configuration will be a magnetization somewhere on this circle. For example, it could be here. This will be our M, which is M bar times some unit vector in that direction. And when we look at fluctuations, there will of course be fluctuations phi L in the longitudinal direction, and also transverse fluctuations phi T. And these phi T in particular, this is for T less than critical temperature, have a zero energy cost. So these are Goldstone modes. And Goldstone's theorem states that when we have n broken continuous symmetries, we have correspondingly n Goldstone modes.
I'm sorry, why do we need to differentiate the word continuous?
Because if we have, so for example, if this is one dimensional, then the minima would be just here and here. We have 2 points, and then there's no other direction in field space, so there's no flat direction. Yeah. So yeah, and that generalizes to any time you have a discrete symmetry, then it's just the minima are at isolated points that are disconnected. Right, so let's now consider the magnetization with fluctuations around the minimum. So we can write m of x as, for example, if we pick a minimum, if we align our basis with the first coordinate direction in field space, this minimum will be, so we can write this as m bar plus by L of x, where L is for longitudinal, and then this is in the one direction. And then we have all the transverse modes. So alpha equals to d by t alpha x. Yeah, alpha. And I'll just write vector by t as, which of course depends on x, as this term. By t alpha of x e hat alpha. So then we can expand all our quantities. So for example, m squared is then just m bar squared plus 2 m bar phi l plus phi l squared plus vector phi t squared. The gradient of m squared is just gradient of phi l squared plus the gradient of phi t squared. So then we can write our Hamiltonian h as integral d dx. First the constant part, which is just our background free energy. So t over 2 m bar squared plus 2 m bar 4 minus mu 0 h m bar. And then we have linear terms, which will be t m bar plus 4u m bar cubed minus mu 0 h times phi l. And then we have quadratic terms, which will be, first we have the gradient term, so k over 2 del phi l squared plus t plus 12u m bar squared over 2 phi l squared, and then the same ones for phi t, which is just k over 2 del phi t squared, so vector plus t plus 4u m bar squared over 2 phi t squared. And then we will have higher order terms, which will be of order phi l cubed and phi l phi t squared. So out of these, so at the minimum, so first of all, the constant terms, since these are just constant, these will just be the background free energy times the d-dimensional volume. This combination, if you recall, vanishes on the minimum. This is the condition for the minimum, so this equals 0. So then what we're left with is basically a kind of scalar field Lagrangian for the fluctuation modes. And in particular, we can write this as, I'll just do it here actually. So this was plus this part. So this is some constant plus integral d dx. And we can integrate by parts. So this is k over 2. I delete this, just phi L of x minus del squared plus something I'll call CL, so minus 2 phi L of x plus again k over 2 by t of x dotted with minus del squared plus ct minus 2 by t of x. Higher order terms. Where we've defined the correlation lines. Which are kind of like the effective mass. Effective masses. CL and CT, which we have the longitudinal ones for phi L, A over CL squared is minus T plus 12 UM squared. And then when the external field equals 0, this is it's little t if the temperature is above the critical temperature, and it's minus 2t if temperature is below the critical temperature. And then we also have the transverse modes. For the phi t directions. A over ct squared is defined as t plus 4u in bar squared, which for external field going to 0 is t, little t, for a temperature above critical temperature, and at 0 below the critical temperature. So for T less than the critical temperature, the transverse correlation length diverges. So the transverse modes become massless. And effectively correlated on length scales that are of order system size. So this is an example of long-range order. And we can define a critical exponent for this. Which is when we say that C for any direction goes as T minus critical temperature to the minus nu. And then from these expressions, when they're not diverging, well, maybe I can, this should be magnitude. So we can consider the longitudinal one below the critical temperature as well. This is near the critical temperature. And then if we look at these expressions, recall that little t is T minus TC, TC. So this tells us that this critical exponent nu equals 1/2 in this theory.
Why do we call that the massless transverse moves is related to the landscape, the system size?
So
Why do we call that the massless transverse moves is related to system size?
Right. So I guess your question is related to like, how do we identify this as a length scale that determines how modes are correlated?
Well, maybe if you can see that the system size length like L is showing to the transverse moves, then we can say that, oh, it's related to the system size, but there's nothing for me.
Right.
Hard to understand.
Sure. So basically, the point is that this, so below the critical temperature, so 1/CT goes to 0, and so then CT goes to infinity.
Yeah.
And I guess, yeah, formally, I mean, this is maybe considering it's easier to consider like a system of infinite size. But of course, in practice, we have a finite size system. So it means that this will, I mean, I guess the correlation length becomes larger than the system itself. So, because this is larger than L, whatever the system size is. So, yeah, so then, yeah, if we accept this interpretation as a correlation length, then it means that the modes are correlated on very large scales. So, okay, I want to now ask, how is everyone doing? Because I have like a little more that maybe would take like 10 minutes, but if anyone has urgent appointments, then
think there's one meeting here
Oh, really?
from 4:30. I really.
Fabulous.
Samsung is gonna.
Awesome.
I think there was on
Oh.
Tuesday there was. On Tuesday there was, but today
Yes.
By the way, we have a longitudinal mode by L, right?
Yeah,
And it's effective mass because negative when temperature is low.
no,
Oh,
because it's -2T, but the little t is also negative.
oh, yeah. But also, when you say that you have a long range folder, does it mean that we can observe the macroscopically? Like with our bare eye?
Yes, exactly. Or with we can see, like, for example, so we're talking about ferromagnetism, then we have some long range magnetism, like over some like human sized light scale, for example. So yeah, in the last 5 or 10 minutes, I want to do one calculation to just show how the correlation functions of these modes behave. So in order to do that, we need to evaluate some path integrals. So I'm going to use the result that for some mode phi, path integral of d phi of e to the minus 1/2 integral d dx, another integral d dx prime, 5x, then some g of x and x prime, which is the Green's function, times another phi of x prime, plus the integral d dx of some h of x times 5x, that this is proportional to, well, some infinite constant, but we don't worry about that. It's proportional to the determinant of this g as considered as an operator to the 1/2. This is a prefactor we don't worry about. And then it's basically by completing the square of these terms, we can integrate this as a Gaussian integral. This is 1/2 integral d dx integral d dx prime h of x, g of x and x prime. Sorry, this should be g inverse here. And h of x prime.
Are we inside a space-time or the spatial manifold?
Spatial manifold too.
Then actually in the last calculation you had computed the dynamical nature of the Boston mode, and it contains some Laplacian operator. But if we are not in the space-time, how can you say that the Goldstone boson propagates at the speed of light?
I didn't say that here.
But you said that the transverse mode become massless.
Yeah, this is an analogy. Yeah, I'm just making the analogy. Of course, in particle physics, we are in space-time, so we can interpret this as a mass. But since we're in space, we interpret it as a correlation length. Right. So armed with this, we can evaluate the expectation value of this field 5x. Which we define as the path integral over d phi of 5x e to the minus beta h. I'll just say, or maybe I should do it properly. No, it's fine. Okay, I'll just do that over partition function. And from this second line, we can see that if we were to take the functional derivative of this thing here, we would pull down, or the functional derivative with respect to h, then we pull down 2 times a half times g times h, and we have to integrate over them. So by comparing that with the first expression, I mean this is simply can be thought of as the functional derivative of log of partition function by with respect to h x. And then this is, as I said, it's the integral d dx prime of g x x prime h of x prime, which as h goes to 0, goes to 0.
So in quantum mechanics, the expectation value comes from the capacity integral, right? But this is because we can quantize it canonically, so it requires a time direction. But we are not in the space time, so how can you say that the correlation function is equal to the path integral?
So because this is just a definition of the average of the field. It's so just the integral of the field with respect to the Boltzmann weight. Yeah. So we see that this step we're using the first line here, because if we yeah, okay, this is, if you like, this is the definition of this average. And then, yeah, to get to this step here, we compare the first and second lines, and from here, this functional derivative with respect to h pulls down a phi of x, which is this phi of x here. And then, so we have, this is just 1 over z delta z by delta h, which is d log z by dh. And then, similarly, we can consider a 2-point correlation function between phi of x and these should all be vectors, phi of x and phi of x prime. Which, yeah, there are more steps, but basically, in the interest of time, we can see it from this one. Just take the derivative with respect to another h. It would be like bringing another phi down, basically. And we can evaluate it from this one. So this is just g of x and x prime. And since the background field is 0, there's no subtlety with the connected or disconnected Green's functions. So in our case, the Green's function. So we have all these the longitudinal mode and all these transversal modes, and they each have a Green's function. Which satisfy k times minus Nabla squared plus c alpha to minus 2, where alpha is L or T. This is for 1, and this is to D. This is acting on some G alpha beta, or x minus x prime. And this is now some delta alpha beta, delta to the D of x minus x prime. And the final part is to just evaluate this. And the strategy is to go to Fourier modes. So and I guess here we're technically taking the system size to be infinite. We can also do with a finite system size, but it's maybe easier. So we define phi alpha of x. We can expand as some Fourier transform over dq over 2 pi to the d. Yeah, e to the I q dot x times phi alpha q. And then we can show that the Hamiltonian then is some constant part plus integral of d dq over 2 pi to the d. So we're just plugging this in to the previous expression and evaluating. And the outcome is that this is then k over 2 times the sum from alpha equals 1 to d. So overall modes, just q squared plus c alpha to the minus 2 times magnitude of phi alpha q squared, where we know that phi alpha of q star complex conjugate is phi alpha of minus q, because we want phi of x to be real. So then from this means that by this kind of construction, we can say that the correlation function of phi alpha of in momentum space of phi alpha of q phi beta of q prime is going to be delta alpha beta. It's only non-zero when they're the same field. Some 2 pi factor 2 pi to the d times delta of so since this thing is phi of q times phi of minus q, this is now delta of q q prime, I guess, if you like. This would no prime here, but I have a q prime, delta of q plus q prime. So that was at q prime to minus q. And this is all times g alpha of q, where from this expression we can read off that g minus 1 alpha of q, g alpha of q to the minus 1 is just k times q squared plus c alpha to minus 2, which means that g alpha of q is just 1 over that. Since by going to Fourier modes, we've diagonalized this, so we can simply invert it. It's just 1 over k times q squared plus c alpha to the minus 2. And then the final step is just to go to position space. And compute now phi alpha of x, phi beta of x prime, and then we just proceed by doing this, doing an inverse Fourier transform using this formula. And so we get that this is delta alpha beta over k times integral d dq over 2 pi to the d times e to the I q dot x over q squared plus c alpha to the minus 2. And then this is, so skipping some ugly details, this turns out to be proportional to the magnitude of x to the 2 minus d in the case where the magnitude of x is much smaller than the correlation length, or it's proportional to magnitude of x over c alpha to the 1 minus d over 2 e to the minus x over c alpha when x is much larger than the correlation length.
Shouldn't we have x prime on the integral, the momentum space?
Which part?
I mean, in the second last line, we have the momentum space integral, and we have exponential of iqx. But I think there should emerge some x prime next to the x.
Ah, I see. So, yeah, I think there's probably a delta to the d x minus x prime.
Maybe can we add an x prime on the exponential? So like exponential of IQ dot X.
Yeah, that's right, actually. Yeah, sorry, I think, yeah, that's maybe the correct answer. Yeah. Yeah, I think it should be this. Thank you. Yeah, so, okay, in this case, this x here is, I just set x prime equals 0. So this is really the x minus x prime in all of these expressions. So in particular, so near the phase transition where actually all correlation lengths become large, this one here, so this x to the 2 minus d, if d is larger than 2, then this is suppressed. So that means that the correlation between fluctuations is small, but when d is 2 or lower, then these fluctuations become very large. And what that means when fluctuations become very large is that will spoil the long range order. In particular, because these are essentially just angles, so they go around they have a finite field space. So that means that the self-interaction fluctuations will blow up at short distances. So it leads to I just need one more line. Actually, maybe I can just put it here. This is related to the Mermin-Wagner theorem, which is that there is no long range order or d less than or equal to 2.